Welcome back. Today we're going to be looking at Chapter 3 at 3.5, graphs and, well, solving them. So for the individual practice, we're going to start with number 1, where we have a program that tells us how to graph the function f of x equals x minus 2 times quantity x minus 4. This code says, declare x real, declare there to be some input. Let f of x be equal to this function x minus 2 times x minus 4. Initialize a list. G, initialize means start, a list such that it's empty for all x such that x is 0, 1, 2, 3, 4, and 5. Find the value of x, comma f of x and add it to the list. Repeat with the next x until you have enough to plot G. So if I want to know what the domain or the input of f of x is, then I type in it's 0 to 5, including the endpoints. If I want to plot the graph, I need both the x and y values, or the f and the x and f of x values. So if I substitute in 0 to here, so 0 for both of these, then my output will be negative 2 times negative 4, or 8. If I substitute in 1, then that's negative 1 times negative 3, or 3. If I substitute in 2, that's 0. If I substitute in 3, that's 1 times negative 1, or negative 1. If I substitute in 4, that's 0. If I substitute in 5, that's 1 times 1, or 1. Now I have a set of points, so I can graph 0, let's see, 0, 8, 1, 3, 2, 0, 3, negative 1, 4, 0, and 5, 1. Once I graph those, or 5, 3. I apologize. That was 5 minus 2 is 3 times 5. 1 is 3. One of the ways to recognize that mistake is I noticed that this is not symmetric, and all quadratics are symmetric. And then right there, that's our graph. Now, normally you would extend it outwards, but because it's defined with a domain of only between 0 and 5, I cut my graph off at 0 and 5. What is the range? So the range is a output value. So the lowest output value is negative 1, and the highest output value is 8. So the range is from negative 1 to 8. Write 3 or 4 sentences describing words how the thought code works. So let's go for it. The thought code sets a variable as a real number, and then defines a set of inputs. Then substituting in each input the thought code calculates the output. Each input output pair is added to a list, then graphed, then plotted. So that's number 1. Let's take a look at number 2. So we already started explaining some of this in class, but let's review it. In exercises 1 through 5, use graphs to find the appropriate values for the solution set to each equation, where these two values are equal to each other. Use technology to support your work. Explain how each of your solutions relates to the graph. Check your solutions using the equation. So what we have right here is on one side of the equation we have a linear equation, 3x minus 2. On the other we have an absolute value equation, which is absolute value of x minus 5. Now I'm going to pick the values negative 2 to 2 because they just give me a good sense of what the graph looks like. And when I substitute each of these values in for 3 minus 2x, I get the green line right here. When I substitute them in for absolute value of x minus 5, I get the blue line right here. The two of them intersect at negative 2 comma 7. Negative 2, 7. That's what we call the solution. One way to show that they are this, in fact, the solution is if I substitute in negative 2 to both sides of the equation, I get 7 or 7, 7 equals 7, or a true statement. Let's recap that with, for example, a problem like this. Here we have 2 times 1.5 to the x equals to 2 times 1.5x. So they still look really similar, but this you'll notice is exponential, and this you'll notice is linear. So I'm going to use the same set of points because they're just honestly a really good set of points for testing data. So for my blue curve, 2 times 1.5 to the x, I'm going to again do negative 2, negative 1, 0, 1, and 2. So negative 2 times 1.5 to the negative 2 is going to be 0.8 repeating. Now I know your calculators say 0.88888 and then 9, but that's really like just a rounding thing. Negative 1 is 1.3 repeating. 0 is 2. 1 is 3. And when I substitute in 2, I get 4.5. Similarly, if I do the same process, again, I'm going to pick the same values, not because there's anything like particularly special, but because these are just very easy numbers to work with. 1 and then 2. So negative 2 is, let's see, negative 2 times 1.5 is negative 3. So 2 plus negative 3 is going to be negative 1. 2 plus negative 1.5 is 0.5. 0 plus 2 is 2. 1 plus 2.5 is 3.5. And then 2 times 1.5 is 3, plus 2 is 5. So those are my two sets of points. I then can graph them. So at negative 2, it's 0.5. At negative 1, it is 1.3, so something like that. At 0, it's 2. At 1, it's 3. And at 2, it is 4.5. And so right there, sketching it in, that's my exponential. Similarly here, I have negative 2, negative 1, negative 1/2, 2, 0. Notice that this right here is in both lists, so we could already spot that as our solution. 1, 3.5, and then 2, 5. Using my handy dandy ruler, I can then draw a straight line. Now I also notice that potentially there seems like there could be some sort of solution up here. And that does make sense. But I can verify very quickly that the solution that is obvious is right here. So there's our solution. And it happens to be 0, 2. I can then verify that by saying 2 times 1.5 to the x to the 0 is equal to 2 plus 1.5 times 0. Anything to the 0 is 1. 2 times 1 equals 2. 2 equals 2. Therefore, 2, 0 is a solution. Now, what about this solution? This solution appears to be something like 4, 9, maybe? I'm going to put that as a question mark. I can test that solution by substituting 4 to both sides. So 2 times 1.5 to the 4, question mark, does it equal 2 plus 1.5 to the 4? And I'm going to type that into my handy dandy Desmos. So that's 10.25. And then 2 plus 1.5 times 4 times 4 is 8. So that doesn't work at all. So at this point we need to use like technology to get us a greater level of detail, because clearly there's going to be some solution there. We just don't know what it is. So there's one equation. Here's the other equation, or the other side of the equation. And we can see there's a solution we found and the solution that looks like there was right there. This approximate solution at 2.77 and 6.164 is the other potential solution. We can only approximate it right now. We don't have the solution itself. Notice how far off that curve is from the data we know to be real. Since we only knew this right here, this area right here, to be accurate, as we get farther out of those, we get less and less accurate. Now let's talk about how to use those types of approximations with number 3. The graphs of the functions f and g are shown. Use the graphs to approximate the solutions to the equations f of x equals g of x. Approximate means that while I can guess where these positions are, I don't know exactly. This one is fairly easy because it's on the line, so it's going to be 2, 1, 2, 3, 4. So that's one possible solution. This one right here, my guess would be it's something like 0.8, 0.6. Now that's a guess. I don't know that to be the case, but I can go ahead and try and figure it out. So my approximate solutions are 2, 4 and 0.8, 0.6. Now that they tell me that f of x is this quadratic right here, and g of x is 2 of x, which is exponential, find all solutions to the equation x squared equals 2 the x. Now, how do I actually do that? Well, some of them are obvious. Like, for example, 2 squared is equal to 2 squared, so 4 equals 4, so x equals 2 is a solution. Now, how do I find the other solution? Let's actually check it out and see if we can figure out how to do that. So we have, let's see, 0.8 squared, that's our x, is that equal to 2 to the 0.8? So typing that into our handy dandy calculator, so we have 0.8 squared, and then we have 2 to the power of 0.8. And they're actually fairly far from each other, except I forgot this is negative. So let's try that again. Negative 0.8. So this right here is about 0.64, and this right here is about 0.57. They are not equal to each other, but they're close enough that I can guess there probably is a solution there. How we would actually go about finding the solution is a separate topic we're going to be talking about, called logarithms and exponentials. But our goal right now is just to be able to use graphs to find solutions. The graphs of a function that involve taking the absolute value of a linear function shown to the right. Both the functions are defined over the real values of x. Tammy concluded that there's no solution. So if we want to highlight here, right here is the absolute value. Here is the linear equation. Are those two ever going to intersect? They don't intersect right now, but if we were to zoom out, would they intersect? One way to think about that is to think about their slopes. Like, for example, this right here has a slope of a rise of 5, a run of 1. So this slope right here is 5. This slope over here, on the other hand, does it intersect a line in 2 places? This is really steep. My best guess is that's halfway, and so this could be as much as 15. Now, if this continues to rise steeply and this continues to rise less steeply, eventually they're going to go and they're going to actually cross by kind of extending out the lines like so, you can see that at some point off the graph, way up there, they are going to intersect. So there is a solution if you extend the graph. Now, looking at the final problem, number 5 here, the graphs of f, a function that involves taking the absolute value, and g are shown below. Sharon said the solution set to the equation f of x equals g of x, where the two are the same, are -7 and 5. Do you agree or disagree? Well, let's look at the values of what happens at -7. So -7, there does appear to be an intersection, and at 5, there does appear to be an intersection. Do you agree or disagree? In this case, I would say I would agree. Now, one of the things that just bothers me about that is the exactly. Do I know exactly that's where the intersection is? Agree as an approximation? Summation. But need to verify algebraically to say exactly the solution. So I'm going to allow you to do the exit ticket on your own. I hope what I put together today was helpful to you. Let's keep working on these together. I'll see you in class on Monday. Bye.